John, thank you very much for a nice introduction. And I also would like to thank you to all of our participants for joining this live webinar this evening. So I hope you can all see my screen now. Okay.
That's great. Glad we can see you.
Good. Great. So today I'm going to talk about the water absorption, gas absorption measurements on MOFs. So briefly, during this talk, I would like to talk about I will give introduction to absorption science. Then I will focus on water and CO2 absorption measurements on magnesium MOF 74 and functionalized MOF 74. I also would like to give examples of strontium MOF for toxic gases absorption. So we will show example of SO2 absorption at 25 degrees and also cycling experiments. And lastly, I will show example of the binary co-absorption of water CO2 on one of the materials. So there is several characterization methods to characterize the metal organic frameworks. So as John mentioned, so in the past I used the energy, so in particular X-ray, so I did lots of X-ray absorption spectroscopy and X-ray diffraction to look at the structure of the materials. We can also use the heat, so in particular calorimetry or TGAs to look at the materials behavior. But in today's talks, we would like to focus on molecules as a probe. So in this way, we're going to look at the absorption technique, and which will provide information about thermodynamics, chemical, and the structure. So we use the matter to probe study of materials. So some of you wonder why we would use probes as molecules to characterize metal organic frameworks. One of the main benefits is that we can actually study MOFs under real conditions. This goes back to origin when the MOF was introduced. There were really promising applications, and when the industry started using the MOFs, they soon after they found out that actually MOFs are not stable under real conditions, to mean ambient temperatures under vacuum, so they need to be kept in the specific conditions. So one of the reasons is now to offer the actually measurements. We can actually look at the stability of MOFs, in particular in the presence of humidity, which is very critical for stability of these materials, and also when they're exposed, let's say, to CO2. So we don't want the MOFs to change the structures. So the probe molecules provide information about the ambient and high temperatures. So we can look at these, also phase equilibrium and study dynamic processes. So vapor absorption can occur in the several ways. So we can have it on the surface. So we can have surface absorption, which is typical with very low absorption, very low, let's say very low uptake. It can become in the pores. We can do between the particles. So then we observe the condensation. Then it can be in the pores or micropores, or some of the molecules can be absorbed into the bulk, or there will be chemical reactions and they can form hydrates. When the probes react with the solid surface, they can get either weakly adsorbed to the surface, or they can penetrate into the bulk of the materials, and so address the molecules coming out of the absorption process. These processes of interaction of molecules with the solid surface can be described by adsorption or absorption. When we talk about the absorption processes, we always refer to physisorption and chemisorption processes. And in terms of absorption, we refer to bulk absorption. So materials goes into the bulk of the materials or into the lattice structure, but then where it can form different where it can formate the, let's say, solvates. In this talk, we only focus on the physisorption processes. We're not going to, so physisorption process, it can be described by weakly absorbed molecules, and it can be physically weakly absorbed molecules can be regenerated. When we talk about chemisorption, the molecules actually react with the bonds of the materials, and they can transfer from one species to the other species. So we can so what other question is like, what can actually learn from these vapor gas absorption measurements? One of the most important answers from these measurements is the stability of the MOFs in the presence of water or CO2. And it was demonstrated by several researchers, let's say from Georgia Tech, that actually, and also by Stefan Gaskell, that actually stability of MOFs is critical for development or storage of these materials, because some of the MOFs collapse when they were exposed to the water, or some of the MOFs actually change the structure chemically when they expose a small amount of CO2, let's say from the air. We can also obtain information about the total gas absorption capacities at different temperatures. And so if you collect, let's say, isotherms in a broad temperature range, we can obtain information about the heat of absorption. We can look at the absorption at very low concentrations. We can go to ppm level. So this is important for carbon capture or removal of volatile organic compounds from the air. We can also look at the information about the kinetics. So we want to calculate diffusion coefficients. So we want to know how fast these molecules can be absorbed by MOFs. And it also provides information about this vapor and gas solid interactions. And lastly, we can calculate which is surface area of these materials if you use liquid nitrogen, which is most common techniques to actually determine the absorption isotherms. So the interaction of a solid or MOFs with a vapor molecule can be described by the adsorption isotherms. So the adsorption isotherm is basically a relationship between the amount of vapor or gas absorbed at different equilibrium pressures at a constant temperature. Yeah. So on the right-hand side, we have the picture of water absorption isotherms on carbon at 25 degrees. What we see here, we have the two cycles. So we have the adsorption branch, which is shown by green and red line, and the desorption branch, which is shown by solid pink and blue line. So what we see on x-axis, we have a relative pressure, which is described as a P or P naught. So P naught is the saturation pressure, or absorbed at operational temperature. On y-axis, we have a change in the mass or the amount of absorbed. So what we see here, so during the adsorption process, we actually step up the concentration of the molecules. And as a result, the amount of the gas absorbed, or vapors in this case, goes up. So the sample is gaining mass. On the desorption branch, we actually step down the amount of the vapor molecules and the weight can go down. Now, the hysteresis is basically the gap. What you see here is called hysteresis. Basically, that's the difference between the adsorption and the desorption isotherms. Now, during these absorption phenomena, several processes occur. So you have the monolayer adsorption, you can have the multilayer adsorption, condensation, bulk adsorption, and hydration reaction. So here we look at the type 4 isotherms, which is can be described by multilayer adsorption, but also the condensation in the pores, which is demonstrated by huge hysteresis in the pores. Now, the adsorption isotherms can be grouped into the IUPAC classification into the 6 main groups. So you can have one for macroporous, non-porous, and weak substrate, mesoporous, and layering. Now, there was also a new grouping released recently by Matthias Thomas and co-workers, where they go more into the detail and explain different interaction of these vapors or gas molecules with the solids. So typically, we look usually for the MOFs, we look at the type 5 isotherms or type 3, depending on the chemistry, how it was dissolved. So microporous are usually typical zeolites, so they have the finite absorption, and type 4 is described by the capillary condensation. I'm not going to describe all of them. Now, how we can actually collect the adsorption isotherms. So there are two main techniques to actually collect, to obtain the adsorption isotherms. So one is the volumetric gas adsorption apparatus. So basically, historically, adsorption isotherms were collected using a volumetric method, spore molecules using liquid nitrogen. And from this data is very powerful data which give information about the porosity and also about the surface area. So it is one of the go-to techniques to obtain, let's say, the surface area and pore volume of the materials. The other way to obtain the adsorption isotherms is gravimetric gas vapor adsorption apparatus, which will be shown in this talk. And this is basically complementary to volumetric system, but is mainly focused on actually understanding of behavior of these materials under more realistic conditions. So when you want to use these materials in the real applications, so once you've done your porosity characterization, then you should go for the gravimetric vapor adsorption analysis to understand how these materials are going to behave in the real conditions, how it can be used for the gas adsorption or other applications. In this talk, we focus on the vacuum gravimetric adsorption analyzer. And the reason is because MOFs or COFs or zeolites, they need extensive outgassing, which is not always possible using traditional methods like the flowing of nitrogen at high temperatures. Also, the system guarantees a clean environment for air-sensitive or moisture-sensitive samples. And as I mentioned, this was already demonstrated that in our apparatus, we can do in situ outgassing and regeneration of the samples, and which is actually very powerful. So we don't, once you load the sample into your analyzer, you don't have to remove it, so you can get the data in situ. Also, when we do water vapor adsorption, there is no carrier gas. So driving force, so the vapors like water, organic vapors, if you study VOCs, are generated by liquid itself at thermodynamic equilibrium at experimental temperature. So the driving force for the molecule is actually vacuum, which is actually pulled from the flask into the system, and then in order to get them into direct contact with the solid material. And this gives us understanding of a pore structure of these materials, in particular the pore size area. So we can actually allow the molecules small enough to go into the pores or the cages of these materials, and this help us to actually design better in the industrial processes. And lastly, it actually allows, so this is dynamic method, it allows us to reach the equilibrium very fast, which is demonstrated even compared to static or dynamic ambient pressures. You get much faster on the vacuum. So how dynamic vapor adsorption or DVS works? Typically, as you would expect, you load, like in your, let's say, thermogravimetric analyzer sample into the metal pan. So it can be either your powder or granules. And in your first stage of all these measurements, either the volumetric or gravimetric, is outgassing of the material under high temperature, high vacuum. So for this, we close the upstream, we pull high vacuum 10-6 millibar, high temperature, and we completely clean the pores or cages of the materials. Once we remove once the materials is outgassed, then the sample is cooled down to adsorption temperature, and then we introduce probe molecules using our mass flow controllers. So for these, we close the downstream, open the mass flow upstream, and we introduce probe molecule of interest, either water or CO2, and then we wait for the interaction of this probe molecule with the sample. And when we reach the steady state, we're going to get a constant flux or water or gases over the molecule, over the sample, in order to reach nice mass equilibriums. If you look at the right-hand side, so I'm showing some graphs. So basically on x-axis we have the time, and y-axis is the weight of the sample. So data here, solid red line is the mass of the sample. Solid blue line is relative pressure. So what we see here, as I described, so initially the material is outgassed. So this sample lost by weight 5% during the outgassing stage. Then we introduce water vapor in the control model at very low concentration, about 0.1% POP not RH, and we wait for the mass equilibrium. So the mass equilibrium is this actually solid red line, which you're reaching actually the plateau. During the and once the mass equilibrium was reached, they move to the next or higher relative pressure step. So as you step up the relative pressure, we're observing the gain in the mass all the way up to 90%. And when we step down the relative pressure, we observe mass loss. And from the equilibrium pressure points, from the equilibrium mass data points, we can calculate the adsorption isotherm, which is shown here, where we actually compare where we plot change or mass gain or weight against the different relative pressures. So this is the typical absorption behavior of zeolites when we observe small hysteresis gap due to the condensation in the pores, because the material made of the clay and there's the condensation of the absorption price. So the adsorption, it can be described nicely by type 1 isotherms, and 50-day pattern, let's say, can be by real side Langmuir or Langmuir isotherm. So this is typical basic principle of DVS. So what it looks like, on the right hand side, we have the picture of DVS vacuum. So you have the set of the pumps, which serves as the basically force to pull your molecules and also for outgassing. Here's got the temperature enclosure. So the temperature enclosure defines your absorption temperature. So we can generate the vapors in the temperature range 20 to 70 degrees up to 90% pure P0. Then we also have a high temperature preheater around the sample, where we can go outgas the materials up to 400 degrees. But we can also perform the adsorption, let's say water vapor up to 150, the gas up to 400 degrees adsorption. And what you can see here is a small flask. This is where you're going to put your water organic solvent. The right hand side is just basically scheme. And I'm going to spend a couple of minutes on this, because especially for co-adsorption, so this system allows you to do 2 vapors, 2 gases, or 1 vapor, 1 gas. For this, we have the 2 muscle controllers, which are used to deliver vapors and gases to the sample. And when the vapor or gas enter the vacuum chamber, it's equally split over the sample side and the reference side. Okay. So what we see here, this is the vacuum chamber. Under dome here, we have ultra balance. So it is symmetrical balance. And from balance beam, we suspended 2 hang down wires, 1 on the sample side, 1 on the left, 1 on the right for sample reference side. On the exit side, we have a butterfly valve, which actually control the residence types or amount of molecules inside the vacuum chamber in dynamic mode. And on the exit side of the valve, we have the sets of the pumps. Now, the pressure is directly measured by 2 paratrons, centaur and 1000 torr. So this is a typical setup which allows you to work in dynamic mode and also in the static mode. Basically, in the static mode, this valve is always closed, and it will work like in the case of volumetric systems that we use muscle controllers to inject the amount of water or gas molecule into the chamber, and then we wait for the mass equilibriums. So when the pressure drops below certain pressure, we're going to refill it. Now, these are the insights of the picture of the vacuum stand, and what I want to show you setup, especially for adsorption. So what can you do? This system allows you to study water and CO2. So it allows you to do pure water absorption isotherms. It allows you pure CO2 absorption isotherms, but I can mix these 2 pro molecules together and perform both CO2 in dynamic mode and the static mode. So what you see, the sample is sitting here on left hand side. Now, to get access to the sample, you under these 2 clamps, this drops down, and you can get access like in the TGA to the metal pipe. So this is very important. And as you can see, this is also inside the temperature control enclosure. We call it incubator, or imagine it's like oven, which control precisely temperature. We don't have an issue with the condensation, but it also is defined, is used to actually generate the vapors in this temperature. Now, as I mentioned, so there's 2 operation modes. One is dynamic mode. And the benefit is when we can go very low absolute pressure, so we can go down to 5 millitorr. So this allows you to do, let's say, water absorption at 60 degrees at 0.02% RH. We can do single dual component absorption and also resistance control. The static mode, which is powerful mode, if you have right type of MOFs to study actually the co-adsorption processes at the constant loading of, let's say, constant loading of the water vapor. Now let's move to applications. So one of the first applications, we're going to look at the water vapor and isotherms and CO2 adsorption isotherms up to 1 bar on MOFs. So, and this is very useful for current climate. So basically, there is a huge interest to study the carbon capture. There is a rise of carbon dioxide in the atmosphere. and which is a major factor for increased global surface temperature. As you can see, the trajectory is if we are not going to do something about it, it's going to keep going up. So for this, there is a need to actually develop the processes or technologies to reduce CO2 in the atmosphere. So there is already several processes considered, like amine scrubbing technologies for CO2 capture and sequestration, direct air capture for CO2 capture from the air. There are already some commercial devices available. Or in this talk, we're going to focus mainly on adsorption-based processes using the MOFs, operating in the pressure and temperature extreme modes. So this is the most interesting for us. So today we're going to look at the MOFs. So there was a lot of excellent talk which give introduction to the MOFs. And I just want to highlight benefits why we want to study MOFs for CO2 capture, because of they get very high surface area. And mainly because the ability to actually study to tune the pore structure of the materials. So these are the most powerful techniques for the MOFs. So in this work, we're going to focus now on magnesium MOF 7.4, which was actually one of the first reported for CO2 capture because it's got higher adsorption capacity. And what we want to do, we want to increase the amount of amine units available for CO2 adsorption by functionalizing this magnesium MOF 74 using tetraethylene pentamine. And the aim of this work, what I'm going to talk today, is actually, so we're going to focus on both CO2 adsorption measurements and co-adsorption measurements. First, before I go further, I would like to highlight one of the things I'm going to talk about is like water adsorption, as I mentioned in my talk, but also want to show the effect of outgassing. Okay, so one of the powerful things about DVS is that they can actually monitor in real time the outgassing of the material. So here we look at one of the MOFs, which was initially outgassed using only high vacuum, 10-6 torr. As you can see, you get certain mass loss. And drying curve suggests the material is already outgassed. And what would you do now? You would introduce your problem, like you will start collecting isotope. Now, but what you can see, I increased the temperature using the preheater to 150 degrees. As a result, my mass loss is actually much higher. And this suggests the material was not completely outgassed. But the reason I mentioned this is actually very simple, because the outgassing of the materials has a huge effect on adsorption capacity and also the stability of the materials. And the reason is you can, if you outgas at quite low temperatures, your adsorption capacity might be too low. If you go outgas materials at high temperature, especially in metal organic formworks, you might destroy the structure. So in our case, we have using this vacuum type preheater to actually outgas materials. So we'll be going to look at the outgassing of temperature on the MOF 74 for water adsorption isotope. So here's a kinetic plot. So basically what we're looking here, we are looking in this plot at outgassing the MOF 74 at 150 degrees. So as you can see, is a huge mass loss, almost 55–8%. And we get nice plateau. And then in a controlled manner, we introduce water vapor, which is demonstrated by this solid blue line. When you step up the pressure up to 90% POP naught, and then we wait at each stage for mass equilibrium. And from these equilibrium points, then we construct the isotope. Now, what you observe here, so if you outgas this magnesium MOF 74 at 150 degrees, you get a huge adsorption capacity. And compared to MOF outgas at, let's say, 250 degrees, which is shown in line green. So basically, what you see, first striking observation is that the MOFs outgas at 250 degrees suggest that the structure was a little bit distorted or collapsed because the adsorption capacity is much lower. And also the desorption, when we perform the desorption steps, lots of water gets trapped inside the matrix of the material, so water is not coming out. Whereas if the materials is outgassed at 150 degrees, the adsorption capacity is higher, but also desorption of molecules is much more of the water molecules coming out of the material. Now we've done the same work on this functionalized MOF 74 at 25. So again, we've done the outgassing 120 150 and 250 degrees. And we see relatively different adsorption behavior. So we again look at the kinetics, what I mentioned, so we can calculate basically diffusion coefficients, how the fast the water comes into the molecules. So we again step up the pressure from 0 to 90, and we go back to 0. So you see the nice equilibriums. And again, what we see, again, the huge effect on outgassing, where you actually see the functionalized MOFs got much smaller hysteresis gap. So the adsorption branch is shown in green, desorption in the pink. So the gap is very small, very similar to, let's say, what you get for like some zeolite shaped these clays materials, compared to same material outgas at 250 degrees. Again, we see huge hysteresis gaps. Water is not coming out of the materials, so the actually structure of material was usually affected by the outgassing of the conditions. So the message from this is outgassing of the MOFs is very important, but is also very critical, the choice of the temperature of for the outgassing of the materials. Basically, as you can see here, you can get very different adsorption capacities for the same material depending on outgassing temperature. I would like to mention not too many researchers mention the outgassing conditions and temperatures, because then it's very difficult to compare from one MOF to the another, because if we didn't start it from the same starting point. Now, this MOF also now we can employ, let's say, modeling, so we can use the Langmuir to feed the data, and we can get a Langmuir constant. So we're modeling. So we also look at the adsorption capacity of MOFs using the CO2. So now I'm not going to go into the kinetics. As you can see, if you go to functionalized MOFs with much higher adsorption capacity compared to original MOF 74 for CO2. So we look at the CO2 adsorption isotones up to 1 bar. Now, we also actually, again, we look into more in details. So first, we look at the MOF 74 outgassing capacity. So basically, you get about 16% uptake. Now, when you have the excess of the amine, which is demonstrated by this green line, and outgassing is 150 and 115, we get much lower. So basically, if you fully saturate this MOF 74 with the amines, your adsorption capacity for CO2 is very low. I mean, one would expect that it might go up when you put more amine sites, you might create more of CO2 site, but that's not the case. But then, if you have actually less than 1% amine, and you use the same outgassing conditions, what is demonstrated here, your actually adsorption capacity usually improve by a factor of 6. So in this case, you get almost 28% adsorption capacity compared to 48% when you have excess of the amine. So as you can see, again, so the effect of outgassing and the functionalization of the mole is huge, depending how you prepare your material, how you're going to outgas your material. So now we're going to move to the co-adsorption measurement in dynamic mode. So the way we done this, I'll show. So we flow over the sample mixture of water CO2, and we went up to 23 torr. And then we look at the effects, so look at the kinetics, and then we can look at the effects of water CO2 mixture. So for these mixtures, we see on this lower slide improvements for functionalized MOFs, as is demonstrated by the isotones here at the bottom. So it's very difficult to comment. But the effect, the improvements we see when you have the mixture 2 to 1 water CO2 water for co-adsorption, that actually functionalized MOF does not show, shows that the sum of the water or CO2 does not stay inside the matrix of the material compared to original MOF 74, where we see observing the hysteresis gap. So the conclusion is actually that functionalization improve the accessibility of CO2 for accessibility CO2, but also improve the water performance, or it improve also the CO2 adsorption capacity of water in the presence of water if you use only 1% of amines. If you use saturate completely the MOF of these amines, then actually some of the CO2 side will be excluded from the adsorption process. My next application will be adsorption of toxic gassing of MOFs. So here, I'm going to look at the MFM 300 MOFs, which was actually prepared by the Jabara group from UNAM in Mexico. And we want to focus on SO2 absorption at 25 degrees up to 1 bar. So once again, the materials was outgas at 25 degrees. And so you can see you get beautiful mass equilibriums at the different pressure steps when we step up the pressure of CO2. So we use the pure CO2. So we go from very low concentrations up to 100% CO2 at 1 bar. And what we observe, we actually get nice type 1 isotherms here. And the adsorption capacity of these moles like 9.4 millimole per gram. Now, we also look at as I said, the stability of the material at the cycling. Well, adsorption performance is very important, as well as regeneration capacity. So what we've done here, so basically we cycle these MFM 300 scandium MOFs under high vacuum. So regeneration was done 10-6 torr for 30 minutes, and then we introduced pure SO2, and we've done the 10 cycles. And as you can see, the adsorption capacity of these MMF MOFs does not change. So the capacity is staying within 9.545 plus minus 0.15 millimole per gram. So it's really good results. So MOF is very stable in the presence of toxic gases, and it remains actually is retained its adsorption capacity. You can do similar studies using, let's say, MIL 101. So in this case, we can keep the water pressure constant at 5.6 kilopascal. And then we just vary the temperature of the sample between 40 and 140 degrees. And as you can see, after 20 cycles, the adsorption capacity of MOFs goes down with a number of cycles. So this is one of the reasons the zeolite are still more used in an industrial scale, because the adsorption capacity doesn't change with the number of the adsorption cycles. And lastly, I would like to introduce you about the binary competitive adsorption of CO2. It's constant loading of water vapor. On this case, I'm going to show the sample of zeolite in order to quantify the amount of which adsorption molecules. So what I will talk you through now is a very simple experiment which can be done in the static mode in our DVS. So basically, first stage is outgassing of the materials, high temperature, high vacuum. Then you leave the material equilibrate at constant pressure of water vapor. So in this case, we use 1.845 volume percent water vapor. We wait for the mass equilibrium. When the mass equilibrium is reached, I bring CO2, a small, on top of it, CO2 in small concentration by using second MFC, and wait for mass equilibrium again. And now from this data, if I subtract my initial water uptake, I can actually calculate CO2 adsorption capacity, and we can obtain this kind of the graph, which tells you that at constant loading of water vapor, at 1.845 volume percent water, I can get about 10 weight percent of the CO2. So this is a powerful method which can be used for certain MOFs as long as they have the correct chemistry, because there are few assumptions we have made. The water cannot replace the CO2, and there are no interaction actually CO2 with the material. So we don't want to have any chemisorption taking the place. Now this brings me to the end of my thoughts. So as you can see, the DVS is very useful, a powerful method for obtaining single components and multi-component adsorption isotherm at different temperatures, and also for studying the water adsorption and gas adsorption isotherms. So if you comply the DVS method with simulation techniques like IST, you can get a powerful data sets for designing of the industrial processes. So last, I would like to thank you to my collaborators, Professor Dara Williams from Imperial College London, Alan Hutton, Leif Bromberg, and Xiao Xu from MIT, and also Ilich Barra and Jorge Balsmada from UNAM for help with the IST simulations. And also, if you are interested, I would like to invite you to our tomorrow session when I'm going to talk about the design of automatic experiments in DVS using DVS vacuum control software, and you can see how you can easily set up this kind of experiment for study of metal organic frameworks. Now, thank you for your attention. And if you have any questions, please, the floor is open for the questions.
Thank you for Thank you for a great presentation there, Vladimir. Do you think we have some time to answer a few of the questions in the chat?
Yes, we have time to ask a few questions. If you guys, I'm very happy to answer. If it's not too late.
Okay, great. There's been several questions submitted, so if you just have a look in the chat scroll, you'll be able to see them labeled if you just want to address them there.
Okay. Okay, so we have the question from Victoria Kulaova. Her question is, does post-absorption H2CO2 measurements using DVS requires first pre-saturation of sample with water vapor and then CO2 absorption? That's correct. You actually got it right. So in this example, I showed two examples. In my last example, in the starting mode, basically, as you described, I need a pre-saturation with water vapor, and then I introduce the CO2 on top of it. Also, your second question was whether I can feed water and CO2 at the same time. That's the correct. So in my previous example, I am able to feed water and CO2 at the same time. But now, when we do this, the challenge is, and I can control pressure inside the chamber. That's not the problem. The challenge is when we feed both water and CO2 at the same time and maintain the pressure is to actually quantify the amount of water and CO2 absorbed, because we can measure, so this is a gravimetric method, and we measure only one mass. So I can't tell from the mass data how much water CO2 is absorbed. So for this, in order to quantify it, we have to either employ IST, so we use the simulation techniques to actually determine the amount of water and CO2 absorbed, and then we compare this data with real experimental data. Or the other option is we are looking at it together with our collaborators in NASA. We would like to edit up, let's say, FTRI to actually quantify it in the real time. So we need another detector to do this. So the other question is from Daniel Dudu. So how do you deal with selectivity, permeability trade-offs? And therefore, in the effect and efficient separation of CO2, this is very good question. So in terms of the selectivity, the way we deal in our case is we look at the structure of the materials and we look at the opening. Like in the simple example, one of the simplest way to look at it is basically we look at the structure and opening of the cages of the pores, and then we look at the kinetic diameter of the probe molecules. And a simple way to do it, if you have the probe molecules which have a huge kinetic diameter, so they might be too big to go inside to the pores. So there's one way to actually deal with the selectivity. Basically, if the molecule is too big to go into the pore, so it's going to be excluded from the adsorption process. If it's small enough, or the pore or the probe molecule is the kinetic diameter is similar to the pore size, so they in that case going to go straight into the pore. So we're going to get the huge adsorption uptake. So it's very challenging in the process for us to actually determine the selectivity and separation. Again, if you want to look at the separation, we have to employ the simulation techniques to actually look more into the detail. But a simple way would be just look at the chemistry of the materials and the kinetic diameter of the materials to look at it physically whether it's actually going to be excluded from the adsorption process or not. Also, the other question is from, sorry if I can pronounce it wrongly, from Peyman Moghadam. Can you also perform the adsorption of toxic chemicals, sulfur capture? Yes. We can perform the adsorption of the toxic chemicals. So we can perform the H2S adsorption. We can do SO2 adsorption, as I showed in my examples. And we can do also the ammonia adsorption. So we can perform all these measurements in our system.
Okay, fantastic. I think that's all the questions we have, Vladimir. Is there anything you'd like to add at the end?
Yes, thanks. I would like to thank all our attendees for listening in to today's webinar. And if they have any questions, please don't hesitate to email me or contact us. We are also open for collaboration. So if you would like to perform some measurements, so I'm happy to do it for you. So please keep in touch and don't hesitate to get in touch with us. We are here ready to help you and help you with all measurements. Thank you very much.
Thank you, Vladimir. I'm sure everyone will join me in thanking you for a fantastic presentation. We would like to now announce the winner of our raffle. This is the giveaway offer we've been running through our MOF app, and this is for the free sample analysis of up to 5 samples. So thank you all for submitting, if any of you are listening in, and the winner of our giveaway has been announced as Patrick Fritz from the University of Fribourg. So we will be contacting Patrick to arrange that. So congratulations to Patrick. I would also like to invite you all to attend our live product demonstration tomorrow at 4:25 European time. This is to demonstrate our control software, a fantastic program we use to design, plan, and automatically run experiments. So it's a fantastic tool for laboratories, especially those running long-form experiments. So we invite you to join us all and find the location for that on our the MOF portal app, and join us tomorrow at the afternoon networking session. I would also like to invite anyone who has any questions or any queries, or who just like to get in contact, to contact any of the surface measurement team through the MOF portal app. I'd like to thank you all once again for joining us, and I hope you really have a lovely evening, and we look forward to speaking to you further. Thank you all.